In these tutorials, we'll now start our study of structures, unions, and enumerations, right, as covered by Chapter 16 in our King textbook. A data structure is just a particular way of storing and organizing data in a computer, right, that makes efficient use of the data. So the appropriate structure of that data, or the data structure, depends on the application. We'll see then there are different data structures that we won't create in this course, but they're called lists, sets, queues, stacks, trees, graphs, hashes, right? Each one of these has its own unique, structure, I guess is the word to use. And based on the way it's structured, it has its own unique purpose. It works better, they work better in some situations than others. For instance, a queue is a first in, first out data structure, right? A stack is a last in, first out data structure. Trees can then store data in a way that makes it faster to search. So there are different methods then, depending on your application, different data structures you want to use will make your application run faster. Right. We've only seen arrays before, right? Arrays are just areas of contiguous memory. So this slide asks, would it be why would it be inefficient to store data on a hard drive in arrays? Well, if you think about it, let's assume you're typing some characters. We know what characters arrays are. Right? So let's think of a Word document as just being a really large character array. So you're wanting to type in a Word document, and you allocate, I don't know, 256 kilobytes for it. And so you're typing away, and you actually just save your work, right? And it fits within that 256 kilobytes, and then you open it up later, and you want to add some more information to it. Well, first of all, what if your work doesn't take up to 256 kilobytes, right? What if your work is only 1 kilobyte? Why would you want to allocate 256? You're going to use areas of your hard drive. You're going to mark that as not being free to store other information. So that's inefficient. And then secondly, as you open up your document and you add to it, right, if your document gets bigger than that 256 kilobytes, then you're going to need more storage. And if you're using an array, an area of contiguous memory, you're going to have to look for a place on your hard drive then where there is enough free memory. Well, as your hard drive gets fuller and fuller, it gets harder for the operating system to find something like that. And plus, it takes time. So something called a linked list is used on the hard drive to store information, where once you start creating your document, say that first kilobyte, it's stored somewhere, and it has an address associated with it. When you open up that document and you add to it and you need more information, well, the operating system just goes and takes a look at the hard drive and finds another area of memory that just needs to store that additional information. And then it uses pointers to link those files together, and we form something similar to what's called a linked list. That's how things are stored in memory on your hard drive, because it's much more efficient. And that's one of the reasons we need to create other types of data structures, just for their efficiencies. Right. We'll see then that structs are just a collection of variables of different types. We're going to use a keyword called struct to make our own data structures. And they're going to have different data members, not necessarily elements. So with arrays, we referred to those as elements, right? If we made an array of 15 chars, well, we could access all the way from index 0 to index 14, and we refer to those as the elements of the arrays. We'll refer then to the data members of a struct, because we're going to have different data types. And so they're called data members. Sometimes they're called fields. Members can have different data types, and we'll access the members by their names, not by their position. So in an array, when we said array index 0, we access that by position. But with structs, we're going to access members by their names, and we'll use the dot operator to do that. All right, here's an example then of how we could declare a struct, right? And it's a collection of logically related data. So if we were trying to keep track of some student data, we might want to have the fields ID, name, and GPA. Those are usually all characteristics of a student, right? You were all given IDs. Normally when you enroll in the university, right, enroll in a school, you're given a student ID. Well, you have your own name. And then as you're graded, you accumulate a GPA. Well, we start with a keyword struct, and then we put everything inside curly braces here. Right? And then we can put as many data members as we need in here, and we can declare them in any order. Right? When we declare them, just like declaring any other C identifier, it has to have a data type and a name. right? So ID is of type int. Name is an array of 16 chars, and GPA is of type double. And then after this, then by giving these two identifier names, we created two structs. One's named student1 that has these 3 data members associated with it. The other one's named student2 that it has these 3 data members associated with it as well. So remember then, keyword struct, data members are always declared inside curly brackets. Data members must have a data type and a name. And then these names that I gave afterwards are just variables of the type struct, right, of that type. Now everything's stored together in memory. So as soon as we declare student1 then has the fields or data members, ID, name, and GPA associated with it. So student1 is our first one declared in memory, and the first available address is 3000. Well, the ID field is declared first, so it's going to get stored in addresses 3000 through 3003, assuming the int takes up 4 bytes. The char takes up 16 bytes, so the name field will get stored in 3004 through 3019. And finally, the GPA field is 8 bytes. It will get stored in 3020 through 3027. So each one of these data members is stored in a contiguous area of memory, right, which will allow us to use pointers later with these. Right. So here's an example, right? This next example is on initializing data structures. Let's just go ahead and pop up this example into code blocks and work with that first so we can see then how that works in the C program. Right. All I've done is I've copied this inside main. Now we'll see the data structures can be formed inside main or outside main. Right. We'll do this first here inside main. If I declare the struct inside main, then only main can access, right, these variables. Right. Now, when I want to access something, an individual field, I can't just say ID. Right? If I say ID, let's assign 5 to ID, well, I'm going to get a compilation error, right? Because the compiler is not going to know what ID is. It says error ID undeclared, right? But we can refer to student1.id, right? So the dot operator is the period, right? So we use the variable name, student1 or the identifier name, and then when we want to refer to the individual data members, we say dot and then the name of the data member. So student1.id would assign an ID value of 5 to that, right? Student1.gpa, well, let's say they haven't taken any classes yet and their GPA just starts out at 0, right? Nothing's been recorded. And if I want to print out that information, right, let's print out some information about student1. Right, student1 ID, well, that's an integer, so %d, right? %.2f for the double. Trying to get that new line character in there, right? And now when I want to print out what's in student1.id, do that student1.gpa, and let's maybe put a couple of blank lines before we print that. In the same way, we could print out what's in student2 as well, right? So for student2, well, the identifier name student2, but student2.id, that refers to student2's ID information. Student2.gpa, right, refers to student2's GPA. Now we're going to take a look at whether or not these are initialized. We compile, good, no compilation errors. Let's build this. All right. So let's do a run to cursor. All right. All right, so what pops up here is locals. Well, here's student1. If I open this up, right, we can see ID field has garbage in it, name has garbage in it, starts with an null terminator, right, and GPA has garbage. Same way for student2. If we open this up, we can see each one of its data members, and it just has some garbage associated with it. But like any other C variable, notice these have not been initialized to anything. Now if I say next line, we'll see that the student1.id field changed to 5. And similarly, right, if we execute that line, student1.gpa is 0. Right, we assign that value in there. And Right, if we were to go ahead and run through this, well, we just see whatever garbage information there was is popping up. And student 1, oh, I got $signs. Well, I need to pay attention to what I type. I didn't want a $sign, right? That needs to be the percent specifier. Sorry about that. Let's build and run. And, all right, and my system's being slow. Right, and I got a bunch of garbage for student2.gpa. Right, I got a ton of garbage for that. Right, got my ID field, and then the other one, yeah, was just overridden. That's just ugly. Right, and I also didn't say GPA here, so we know what that is. I didn't put a label on that. Right, now the important lesson here was, if we don't initialize these to some value, each one of these data members are not initialized. They have garbage in there. When we want to work with these data members, well, we use the name. All right, so we have a struct named student1. Student1 has 3 fields or 3 data members: ID, GPA, right, and name. Right. Now, what happens if we have an initialize then name, right? A character array. Can we say something like student1.name? Can I just assign some string to that? Right. Let's say, oh, let's call our student Alf, right? Can we do that? Right. Based on your knowledge of C so far and initializing strings, do you think this is going to compile? No, it does not, right? Assignment to expression with array type. We can't just assign to a string array, anything like that. What we can do is there is a function called string copy, right? When we want to then copy something in, we're going to say student1.name. And now if we want to copy in Alf, right, we do that. We don't assign it back here. Right, and then what we need to do in order to use the string library, string copies inside the string library, I need to include that. So string.h. Now, right, if we compile, that compiles for it. And so if we want to print out the name information, let's add that as well, right? %s to the string, right? Student1.name. Let's just comment out the student2 stuff that we're not using, right? That's been uninitialized. Let's build this, and right. And it's complaining about my unused variable. Right. Let's run. Right. So we can see then when we run, the output student1, their ID was 5, we assigned 5. The name that copied into the string was Alf, right? And their GPA is 0. And what we learned then at this point was, once again, when we declare student1 and student2, these have garbage in there, right? We'd already then accessed the ID field and GPA field. We use that with the identifier name, the dot operator, the period, .id, .gpa. Because name is a character array, we had to use the string copy function then in order to then put something other than garbage inside the string. Right. The other way we could have done this, outside of string copy, right, is we can have the user enter name. So enter student name. Right. Let's prompt the user to do that. And now we can use scanf. So if I use scanf, well, I want to read this in as a string. And if I say student1.name, oh, need to stop this other one from running. All right. Right, it's not happy about my other unused variable. No, but now if we build and run, all right, enter student name. All right, well, let's do something other than ALF just to show it doesn't put ALF in there. Oh, let's see. I don't know why I'm at a loss for names. How about Snoopy? All right, we'll put Snoopy in there. All right, so now we see that we can read in then the student name, Snoopy. All right, we use %s student1.name. Well, remember then, because name's an array, this is already, by using it like this, it's the location, pointer location that scanf needs, or the address location. So we just say student1.name, like we would with any other array if we were reading a character array, if we wanted to store a string in it. So you've seen a couple of different ways. If you have something where you just literally need to copy a string into it, you need to use the string copy function, right? Otherwise, if we want to read from the keyboard, we use scanf, we use %s, just like we would with any other character array, except we have to say student1.name in order to get to the name field. Right? So that's one way then of initializing after the declaration. But if we go back then to the lecture slides, we'll see that we can create an initializer list as well. All right, let me pop that up. So we can use an initializer list similar to what we did with arrays when we declare this. So now when we declare the struct, right, if we go ahead and inside curly brackets, we put the initializers, then this is an ordered initialization. Whatever we have first gets stored in the first data member. So 101 will get stored in ID, right, for student 1. Eric Cartman will get stored, initialized into name, right? And then 2.50 will get initialized into GPA. For student 2, right, if we initialize this, they'll get the ID number of 110. So order, first one goes into ID, second one goes into name, third one goes into GPA. So this is an ordered initialization, right? And that's what we'll see after that. Right? So if we were to just copy this into code blocks, here, right, taking me a minute to copy, right, grab an extra curly brace. All right, so now I don't need to do any of this. We can go ahead then and show our student 1 and student 2 information. We pop this up. All right, so we can see then, actually, so I hadn't updated the printf to show the name. Let me do that. Right. Name %s for the string, the character array. I need to now put student2.name here. Right, we build and run, we'll see both of those fields. All right, so if we know then when we create it what we should initialize it with, we can do that. If we don't know what to initialize it with when we create it, once again, we could just use scanf. If we go back to, let's just do student 1. Like we can with anything else. We're going to say enter student ID. All right, the student ID field, right, is an integer, so %d, right? And now we need to give this the address of student1.id. Similarly, for the GPA, right, enter student GPA. And I want to change this to GPA. And because this is a double LF, and then the same way for name. All right, enter student name. And let's maybe make this a little bit bigger. That's a %s, and let's limit that to 31 characters. Now I don't need the address. I can just say student1.name. All right, and let's build and run this. So enter student ID. Well, we were initializing with 101 before, so I'll use 101. Eric Cartman. Well, now I'm only going to grab part of the name, because notice if I type Eric, right, if I type a space in Cartman with %s with scanf, I'm only going to get the one field, so I'll just type Eric, and then 2.5 is my GPA. We get that information back out here, right? Now, if I want to be able to read in both names in here, I can always try gets, and then I can say, well, let's give this student1 dot name. Right, build and run. So once again, 101. Now I can say Eric Cartman. I grab both these strings. And they didn't end up with anything in my field. Yeah, I knew it wasn't going to like that as a pointer. Which I shouldn't have. Let's compile. I didn't see any warnings before, but I wasn't paying attention. All right, what am I doing wrong with gets here? I think it's relating to the new line character. All right. Let's remove the new line character. Wow. So get char returns an int. I'm going to cast it to a char. Well, that's not equal to my new line character. Just remove that from the string. All right, so student ID 101, Eric space Cartman. Hit the enter key, student GPA 2.5. All right, so that didn't work for me before because I had not removed the new line character, right? Well, I was not doing this. Then what gets does is gets terminates when it sees the new line character. Since that new line character wasn't removed here, gets wasn't storing anything. And then the next scanf was failing, right? If we do a little build and run on that again, right, with a gets like this. I don't know why my system's so slow today. 101, press the enter key. Well, then for student name, right, it just read that enter key press, didn't let me read anything else. The next thing it's doing is prompting me for the GPA, right? So because I'm entering multiple things, I forgot the fact that gets is going to terminate when it sees that first string or that first new line character. I had to go ahead and make sure that I remove the other one from the string, right? Did not mean to provide you with that extra distraction, although it's a good reminder of how annoying and painful scanf and gets can be, right? Eric Gartman 2.5. All right, back to our working example. All right, so that then showed us how we could use either scanf, right, or gets to read things in. We learned a lesson, right, that I had forgotten about the new line character, and we stored this information inside our struct. Right. We saw how to do that then with an ordered initializer list as well. And then there's something called a designated initializer list. So let's go back up. Right, this was ordered. Right, this first one was in the list was the first one assigned. Second one was the second one assigned. Right, third one was the third one assigned. Otherwise, you can specify what you want to assign by designating it. So in this initializer list, if you say .id equals 101, then the ID field will get 101. .name, Eric Cartman, we can assign that. .gpa. And the thing is when you use these designated initializers, you don't have to then initialize in order. Right? Here I could say .name equals Leopold Stosh first and fill in the name field. .gpa, fill in the GPA field. .id, fill in the ID field. So I can change the order than when we use this designated initializer list. Sometimes that's easier to check for correctness because you know exactly what field you're trying to initialize. Right? You don't have to change the order, right, but you can. Right. So we're going to then take a look at example 1 that I gave you, which is actually just using this same designated initializer list. Now let me pop that up. All right, here's the example 1 you were given. All right, so I'm using name length. The macro here is 25, and then creating the name field to be 25 plus 1, leaving an extra for the null terminator. All right, student ID, I'm using that student 1. And student 2, I'm using that designated initializer list we saw in the last slide. And then I'm just going to print out some information here. If we build and run, all right, we're just going to see that the designated initializer list works as well, but not with 2 pound signs in my code for not fully erasing all of the last example. Okay, and so now we see then we have the information for student 1 and student 2. All right, so this showed you then that the designated initializer list worked as well. All right, let's take a look then at another concept related to structs here. All right, so student 2, we gave the name Leopold Stosh, right? And if you watch South Park, you'll know that Leopold normally goes by Butters, right? Even his parents call him Butters. And so after setting up our record, we wanted to go ahead and change his first name in there. But we're going to use the string copy function again to make that change. Right? And let's say that we also want to change student1's.gpa. Let's go ahead and do that, and then we'll do the exercise of calculating and printing the average GPA of both of our students. So what we said was here, we want to just go ahead and make a change to his name after we initialize it. All right, and actually notice how we're writing sort of the same code twice here. Let's write a function then to print out the data. So we're going to say void print student info, right? Or we'll just call it print student. And if I pass this something of type struct, I'm going to you know what, we're going to have a hard time doing that because I haven't explained 2 or 3 other things yet. So let's not do that quite yet. I'm getting ahead of myself. And we've declared this inside here. I'm going to have, we'll explain that in the later part of the lecture. Let's just go ahead then, and we're going to say, right, change Leopold stop to butters. All right. So we say string copy, right, and he's student 2, student 2.name. And what we want to copy into that is butters starch, right? And we'll just say printf, right? Updated name. And he's student 2.name. And if we build and run this, and I should have left some spaces. We see updated name is butterscotch, but let's pretty that up. All right, let's go ahead and use all 25. Let's just again build and run just so to make that line a little more legible here. And I didn't add a new line character at the end. Not on my game today, I don't think. But you can see we went from Leopold Stodge to Butterscotch. We did that with string copy. Right. Let's then, right, find the average. We're going to print out, right, average. So let's say they're the only 2 in the class, that the average class grade, right, is, let's give it 2 decimal places. Yeah. A couple lines all by itself. And all we need to do is, well, we can just say student 1. Student 1 dot GPA plus student 2 dot GPA. Right, and if we divide that by 2, we would get the average grade. Right, and these are just to give you some examples of how you access the fields with the dot operator, right, with the period. Right, and so we get actually the average class grade. What did I mess up? 4.0. Oh, I used a 1 here instead of an L. Oh, I'm sorry, I used an L. We don't use that in printf. Right, only in scanf for a double. All right. Now we get our correct average. Right. Calculation was correct. My printer specification was not with the L for the double. It should just be the F. All right. And so once again, we use the dot operator just to get to those fields. We're going to then take a look at how to create structs. These are actually, this is also sort of anonymous sort of struct, right? In terms of, we're going to eventually then create a type definition for that. But the first other thing we want to do is we want to take a look at some other property of structs. How do we compare one struct to another? Right? We can't use C relational operators to compare 2 structs, right? We can't write something if student 1 equals student 2. That's not defined by the C language. We can't see if a student is greater than or less than another student. We can check their individual member fields, right, to see if they're equal. And so if we were to say, does student 1 equal student 2, we're saying, does Eric equal Butters, right? So once again, comparison of structs is not defined by C. Right? If we want to do that, we have to write our own function to do that. So we can't use relational operators with the structs, with the identifier names of the structs. Right? All right. let's pop open then this. Okay. Let's go ahead and show this. And then we'll go to example 2. We can't say if student 1 equals student 2. Right. If that's true, we can have a no-op going just to have good syntax. So if we say compile, right, we're going to get an error that says invalid operands to binary operator. Right. Have struct anonymous compared to struct anonymous. We can't do that. So later, if we need to write something like that, we can. Literally, we'd have to write something, you know, we'd have to say if student 1 dot ID equals student 2 dot ID and student 1 dot GPA equals student 2 dot GPA. And then we'd have to say, and remember our string comparison? Let's compare student 1 dot name to student 2 dot name. And that, when they're equal, returns 0. If all that's true, then we can say, all right, put something like student 1 equals, is the same as student 2. And we know that's going to fail. All right, but that's what we have to do. If we wanted to then specify what our idea of equality is, we'd have to individually compare all of these fields in order for that to be true. Right. If we build and run this, all right, we don't get any output because that wasn't true. And it's telling me comparing floating point isn't a safe operation. They're right. And implicit declaration. So I got rid of the string library. Here. And now to show that this is true, all right, this would work. Let's just make 2 Eric Cartmans. I'm not sure if the world is ready for 2 Eric Cartmans. Right. But let's see. From a C programming standpoint, all right, since we initialize both of those are the same, this proved to be true. Student 1 equals student 2. Right. So it gets more cumbersome when we start writing a struct because we can't use all of C's operators. A lot of C's operators are meant to work with the primitive data types. We'll find then that we have to define what our own ideas of equality, addition, subtraction, certain things are when we're referring to the entire struct. All right, now let's take a look at assigning one struct variable to another. All right. What happens then if we have student 1 and student 2 and we try to assign student 2 to student 1? Well, we're going to find out that's a legal statement and it's going to copy all of the data in student 1 into student 2 and it overwrites student 1's data. And it does this even for the arrays. And that's a fairly handy feature, right? Because we know that if we have 2 arrays in this example, if we have A and we have B and they're each of the same length, we can't write something like assign B to A, right? But when arrays are within structs, then we can actually copy that. They'll actually copy over. This will work. So this is one of these other little quirks of C that you have to remember in order if you want to be assigning one struct to another. Right. Let me pop open example 2. Let me get rid of this. So example 2. It's the effect of assigning one structure variable to another. I'm just going to build that. All right, while we go through this. All right, so name length is 25. I've included standard IO. Here's our struct inside of main. Here's our 2 students, 1 and 2. Right, with our designated identifier list, same thing we had before. We're going to print out then the original data, and then we're going to assign student 1 to student 2, and we're going to print out the information after that assignment. So most of this is just printing out the information. All of this code here, here's the important part, then assigning student 1 to student 2. Right? And so if we run that, right, so here's our original data, student 1, student 2, after the structure variable assignment. So after we said, let's assign student 1 to student 2, right, we end up then with 2 Eric Cartmans, right? And it says, oh no, not 2 Eric Cartmans, right, in the end. So that is just something that is really unique to structs. It's often difficult to remember, right? Unless you're working with them all the time and you need to do this. Likely this is something you'll have to look up whether or not that's legal to do, but it is legal, right? And it can come in handy, the fact that it copies over all that information. All right. Last part of this particular lecture, then, before we start the next topic with structs, is data member scope. Right. Here's something that you'll probably likely find confusing and you'll avoid doing. But each structure has its own separate namespace, right, for its members, and each structure represents a new scope. Remember, block scope then relates to anything declared inside curly brackets. So these fields are declared inside these curly brackets here. Right. Well, outside of there, you can use variables that have similar names, name, ID, GPA. Because remember, with these, we're going to refer to this as student1.id, student1.name, student1.gpa. So you can use the names name, ID, and GPA then inside main, simply because they're defined outside the scope of these braces. And like I said, you can do that. You can do that if you want. If you find that confusing, you can always give them other names, but just be aware of the fact that this relates back to scope. Right. All right, in our next lecture, we're going to talk about structure types, what a tag is, and what a type def is. And we'll find out that we'll be able then to declare these globally. We'll be able to pass them to and from functions once we learn how to do that. So that's the topic of the next video.